First of all, can everybody hear me okay? Loud enough? Okay. Well, first, let me begin by thanking the organizers for inviting me. It's really a pleasure to be here. I guess the other thing I want to say is, also following the remarks of Professor Tauber this morning is that I'm very honored to be able to lecture to you and to maybe play some role in helping to shape, and I hope in a positive way, you people, the future of statistical mechanics in India. So I'm going to be giving what I would call, there's the title, Non-Equilibrium Statistical Mechanics Elementary Examples. And so let me begin, let me just say that, let me underline elementary. My feeling about non-equilibrium stat mech is that it is a field that has no overarching formalism. So when you learn undergraduate, your first course in stat mech, you learn about the partition function, you learn about thermodynamics, you learn about that the overarching principle is minimization of free energy and everything follows as a consequence. In non-equilibrium processes, there is no fundamental principle. And so I think it's simpler in my mind to understand stat mech, non-equilibrium stat mech, by looking at a number of paradigmatic examples. Examples that are simple conceptually, but as you'll see, they're very beautiful when you work out some of their consequences. So that's my approach, is that I want to present to you a number of examples. They're all over the place. They go from complex networks to aggregation to adsorption to phase ordering kinetics. But nevertheless, I hope you see an underlying unity in the tools that you use to attack these problems. Okay, so as I understand in the preliminary courses, you learned about the master equation. And the master equation basically is that you have a bunch of states in an abstract state space, and there is an underlying equation that says, how does this probability distribution evolve? The probability of being at a given point in state space is equal to, or the change in the probability is equal to the sum of the transitions into that state minus the transitions out of that state. So that fundamental equation is basically my starting point for all of the examples I'm going to present. Okay, so let me begin then by talking about my first example. So one is aggregation. So to introduce the problem, let me mention to you that I was walking along the sidewalk 2 days ago, and I tripped on a rock, and I did a swan dive on the sidewalk. And when I got up, my hand was bleeding. Why did I not bleed to death? And the reason I didn't bleed to death is because there's a process known as aggregation. There's blood clotting, and if my blood didn't clot, anytime any of us would cut ourselves, we would bleed to death. So aggregation is a very fundamental and ubiquitous non-equilibrium process in which clusters form to make larger clusters. They stick together irreversibly. And so I can represent aggregation pictorially as the process that I have a cluster of mass I and a cluster of mass J, and they come together to form a cluster of mass I plus J. And the rate at which these guys come together is governed by something called the reaction rate or the reaction kernel K sub ij. So as I mentioned, this aggregation process is what prevented me from bleeding to death. It also is responsible for making cheese, the curdling of milk. It's responsible for the formation of the solar system because planetesimals aggregate to make larger planets. It underlies all kinds of chemical reaction kinetics. So it's a ubiquitous process, and the basic question that I want to ask is, what is the concentration of clusters as a function of time? So the basic observable is what I'll call Ck of t. So this is the concentration of clusters of mass K at time t. Sometimes I call these things K-mers. So we'd like to understand how this cluster size distribution evolves. Now, the way that I'm going to attack this problem is I want to try and get some understanding in the simplest possible situation was the so-called mean field limit. So in the mean field limit, I'm going to invoke a couple of assumptions. And so we can think of these as the mean field limit, MF. I'm going to assume that there's no shape degrees of freedom. That is, I'm thinking of my clusters as like, say, spherical droplets. And when they come together, they make another larger spherical droplet. So the only degree of freedom is the actual cluster size. There's nothing else in the arguments here. Furthermore, there's no space. So I'm assuming that my clusters are very well mixed, which isn't what happened when I fell on the street, but we're thinking of like a reactor where things are mixed rapidly. And so there's the concentration of clusters does not depend on any shape. It doesn't depend on any location. It only depends on the size of the cluster. And finally, I'm going to make the low density limit approximation. So this is a simplifying approximation that allows me to write the reactions in terms of only bimolecular reactions. Because if initially there's a very high density of clusters, as they aggregate, there's fewer and fewer clusters, and the bimolecular assumption becomes better at long times. So since I'm generally interested in the long time limit, I'll make the low density approximation from the very beginning. So now let me write down the master equations that describe the evolution of the cluster size distribution. So CK dot. So how can the concentration of clusters of mass K change at any time? Well, there's, again, just as in the, presumably what you got in your course one, there's input into CK and output. And the input terms are I can take a cluster of mass I and mass J such that they add up to K, and any combination of those will contribute to the gain of concentration of clusters of mass K. So there would be, I have to sum over all combinations of I and J such that I plus J is equal to K. And then I would have here Ci times Cj. So the, again, in the mean field approximation, I'm just assuming that the rate at which two clusters meet is proportional to the product of their concentrations. There is the reaction rate, Kij. And then there's a little bit of a subtlety because I have to put a 1/2 out in front to avoid overcounting, because there are two terms that contribute to C sub, say, 37. There's a C23, C14, but there's a C14, C23. To not overcount, I should put a factor 1/2. So that represents the gain term. But then there's a corresponding loss term, because if a k-mer bumps into anybody else, then I lose k-mers. And so there's another term here, which I can write as a CK times summation over all I, Ki, K, Ci. So these are the rate equations that describe aggregation. And so the goal of this lecture is to try and solve this equation for a number of paradigmatic situations. Now, one more thing just to mention here is that I've written this in the framework of discrete masses. So this might be appropriate for polymerization, where there's a monomer and then there's dimers and trimers. There's like a sort of a smallest possible mass. But if I was thinking about the astrophysical application, that I could have, you know, clusters of any size ranging from like essentially single atom up to like a size of Jupiter, then maybe I should write this in the continuum formulation. So this is the discrete equations. Continuous. I might write something like Cxt is equal to 1/2 an integral from 0 to x dy, C of yt, C of x minus yt, k x minus y. That would be the gain term. And then there's a loss term, an integral, say, from 0 to infinity, Cxt, kxy, cyt, dy. So that would be in the continuous limit. That's just the direct correspondence of this. Okay, so before we make any progress, we have to make some assumptions about the form of this reaction rate. What is it? And so let me first give you a feeling for like what is a reasonable form for the reaction rate. perhaps the simplest case that one might think about is so-called Brownian aggregation of particles in solution. So the Brownian kernel oh, sorry. Thank you. Yes, I tend to be absent-minded, so if I forget something, please feel free to correct me, and please do interrupt me with questions. So in the Brownian kernel, we're thinking of particles that are diffusing around in solution, and when they come together, they bump into each other and they aggregate. And it turns out, and I guess, I don't know if this was done in the preliminary lecture, and if it was not done, maybe I'll do it in a tutorial, but if you just have diffusion-limited reactions in solution, the reaction rate K is just equal to D radius to the, let's do a general dimension, D minus 2 power. So this is what's called the reaction rate. And so this is if you have like a sphere of radius A, and you have diffusing particles that are coming to the surface of the sphere. This is the rate at which particles will hit the sphere. And in order to generalize this or to extend this to Brownian aggregation, we should think of not just one sort of stationary particle with lots of little, pardon me? A is the radius. So I have in mind here, I have a particle of radius A, and there's lots of little diffusing particles that are hitting the sphere, and this is the reaction rate. You're worried about dimensions. Well, so it's not a problem because this is C over T, this is C squared times K, so you just have to ensure that the reaction rate has the units such that C squared times K is equal to C over T. And in fact, that's what this thing is. It has the right units. Anyways, I just wanted to say that from this we can infer the following, that if I now have particles all diffusing around, this, for a result of a single absorbing sphere, this is sort of the obvious generalization. It's di plus dj times ai to the d minus 2 plus aj to the d minus 2 power. And now let me live in 3 dimensions, just because that's where life mostly takes place. What is the diffusion coefficient of a cluster of mass I? It's proportional to the inverse radius. So here I'm assuming something. Let me just finish my sentence and then I'll answer your question. So this is 1 over I to the 1/3 plus 1 over j to the 1/3, and this is this is I to the 1/3 plus j to the 1/3. Question? Yes? In 2 dimensions? Well, 2 dimensions is very special, and it's outside the regime where this works. It turns out that in 2 dimensions below, this theory of the reaction rate actually blows up, and there's a singularity that happens there. So this should only be, you should only take this seriously for D specifically larger than 2. And if you want to see what happens for D 2 and less, I mean, that's also something maybe for a tutorial. Anyways, the point about this is that this is roughly 2. Well, it's equal to 2. When you multiply this out, there's I to the 1, there's 2 terms that complement each other, and then there's terms that look like I over j to the 1/3 plus j over I to the 1/3. So here, I'm now going to wave my hand and say, well, if the clusters are all growing and there's a characteristic cluster size, then I over j is roughly order 1, j over I is roughly order 1. And so overall, we can think of this as roughly equal to a constant. Actually, that turns out to be wrong. But nevertheless, it's clear that a simple case that the simplest case we might deal with is a so-called constant kernel aggregation. So what I want to do for the next while is to just delve into the problem of solving the constant kernel aggregation problem, because first of all, it's a beautiful application of the generating function approach, and the result is very generic and very, very useful. So I'm going to now specialize in the case of constant kernel. and again, because the kernel is constant, I can choose that constant to be anything I want. And for reasons of convenience, I'm going to choose that constant to be 2, just for fun. So Kij is equal to 2. So let's write down the equation for the discrete system. So we have Ck dot is equal to summation Ci Cj, maybe I'll put a prime here to denote it's a restricted sum. Then I have minus 2 Ck sum Ci, unrestricted sum. And to get a little feeling for this, let's write down the first few of these equations. So C1 dot. Well, there's no way to make a monomer from nothing because the monomer is like the smallest thing. So this is equal to minus 2 C1. This sum appears over and over again. And what is this? The summation of all the cluster concentrations of any size. That's just the number density. So let me define this thing to be the number density. So I have minus 2 C1n. If I look for C2 dot, well, there's C1 squared, so C1 squared minus 2 C2n. C3 dot is equal to, so there'll be a term C1 C2, C2 C1. So there'll be a term 2 C1 C2, because there's 2 such terms, minus 2 C3n. C4 dot. And I'm going to stop writing after this. So there's a term which is 2 C1 C3 plus C2 squared minus 2 C4n dot, 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 dot. So exercise, if you are a masochist and interested, you can solve these one by one. Notice that all of these equations involve n, but let's just look for fun at what is the equation satisfied by n, which is the sum of all the ck's. So from this equation, if we sum up over all k, we'll get the equation n dot, which is equal to the summation over all k, ck dot, the dot over here. So we take these equations and sum them all up. When we sum them all up, here the restriction that I plus j equals k goes away because we're summing over all k. So we basically have 2 unrestricted sums, sum ci, sum cj, which is nothing more than n squared. Here is n. Here I have another sum k over all k ck, so that's another n, but I have minus 2n squared. So the equation for this is minus n squared. So this is an easy equation to solve for. And for everywhere in this lecture, I will assume the monomer-only initial condition. I start with a system of only monomers, and in this case, the solution for this equation is n of t is equal to 1 divided by 1 plus t. So now what you can do as an exercise is take n as 1 over 1 plus t, plug it into here, solve for C1. Now you have C1, you can go to this equation. It's a simple differential equation for C2, solve for C2, solve for C3, solve for C4. You'll see a general pattern, and you'll get the general solution. So that is actually an exercise that I leave for you to do. But what I'm going to do is a slightly different approach. So first of all, before I solve the general equation, I'm going to do a little bit of a preliminary because, you know, in many problems in non-equilibrium statistical physics, we start with some complicated looking master equation, and we want to solve for a probability distribution. Sometimes a probability distribution looks a little intimidating to start with. In order to get a feeling for like how to attack the problem or how to even start, it's sometimes useful to look at equations for the moments of the distribution. So it's like the same as like when we are teaching classes and, you know, I have to give all of you people a grade. And so one thing I might say is, well, the average grade in this class will be a B+. But that could be half the class gets an A and half the class gets a D, or maybe everybody gets a B+. So the distribution of grades is, the fundamental thing that that you individuals might care about, but the average grade is maybe easier to compute. So let me look at the moments of the cluster mass distribution. So moments, let me call these things M sub n. And this I'll define as a summation k to the power n ck. And let's look at low order moments of the distribution. Notice that by definition, m0 is the same as what I called n just above. So let's look at the equations for the low order moments. So m0 dot, we've already done it, but let me do it again. So what I have to do is I take my fundamental equation. I want to multiply by k to the power n and sum over all k. So for n equals 0, so maybe I'll put n equals 0 as the header out in front. So when I multiply by k to the 0 and sum, so on the left-hand side, I just get m0 dot. And on the right-hand side, well, you know, I again have m0 times m0 minus 2, I'm sorry, m0 times m0, so that's m0 squared. Here I have 2. Here was an m0, m0 again, so I have minus 2 m0 squared. So I have m0 dot is minus m0 squared, and we had that m0 is equal to 1 over 1 plus t. Let's look at the first moment, m1 dot. So we now take k to the power 1 ck. So on the left-hand side, we'll just have the first moment. And on the right-hand side, so we put k here. But notice that k, by construction, is I plus j. So that's the same as putting I plus j in here. And now when we do the summation, there's a term I ci cj, and then j ci cj. And let's look at each of those two terms in turn. So ICI is M1, when I sum up over all I, and CJ was M0. I have two identical such terms, so I'm going to have here 2 M0, M1. On the right-hand side, when I multiply through by k, here is M0, here is a 2, here is KCK, which is M1. So I have minus 2 M0, M1 equals 0. That's good, because we've now verified mass conservation. By construction, KCK is actually a very special moment. It's the total mass in the system. It's the number of clusters or the concentration of clusters of any size times their size. So by construction, this is just the total mass in the system. And so in some sense, this check that the first moment is conserved is a good test that you've actually written down the equations correctly. And in more complicated situations, you know, when you're not sure, did I keep everything correctly? Was I a good accountant at not cooking the books? This is the way that you check that you actually have the right answer. Let me do one more moment. Let's look at M2 dot. So now I would multiply through by k squared. So we put a 2 here, and I'd put, you know, times k squared over here. So let me do the second term because it's a little simpler. So I'm going to have minus 2 M2, M0. So here's minus 2, okay, M0, M2. Here, when I have I plus j squared, so there's 3 terms. There's I squared plus j squared plus 2ij. I squared ci is the second moment, times cj is the 0th moment. I have 2 such terms like that. So there's a term here which is 2 M0, M2. And then there's a cross term, I, 2ij. And so there'll be a 2 ICI, which is the first moment, JCJ, which is the first moment. So 2 M1 squared. So this cancels, but since the mass is conserved, the mass is a constant, and the way that I'm normalizing things, I'm considering the total mass to be 1. And so what I get from this is 2m1 squared, which is just 2. And so what I get then is m2 is equal to 1 plus 2t. So again, I'm starting with monomer-only initial conditions, so the second moment is 1 at t equals 0, and then this is how it grows. The average cluster size, so from this we infer that the average size grows linearly with t. So that at least gives us a feeling that for this constant kernel aggregation process, the average cluster size is growing linearly with time, And that's what we want to actually extract more rigorously. Now, one thing before I actually go to like a real mathematical solution, just mention that oftentimes in these sorts of problems, it's really useful to try and just do some kind of order of magnitude estimate to just try and get some intuition in the process. And so let me show you an order of magnitude estimate to determine the average cluster size. So let's just estimate for average cluster size or average cluster mass. Let me call this average cluster mass S. And again, I'm thinking in terms of like a mean field picture. And so let me discretize this mean field picture in which I imagine that my clusters are living on a complete graph where every site is connected to everybody else. And when a cluster hops, it's going to hop to another site on this complete graph where there may or may not be a cluster. And then I ask, how does the cluster size, or how does the average cluster size change? So I want to try and estimate the change in the average cluster size per reaction event. So if I imagine that there is kind of a typical cluster size, so I start with all monomers, and after a while there's like, the average cluster size is 10, and so there might be a distribution around 10, or then a little later this typical size is 100, and there'll be some distribution about 100. And so when I have a typical cluster size S, I want to ask, how does a typical cluster size change? So if there is a well-defined cluster size, then when two clusters meet, the change in the cluster size will be of the order of S itself. Right? So if I have clusters of size 100, so when I bump into somebody else who weighs 100 pounds, and we join together, and now we weigh 200 pounds. And how long does it take, or what is the time increment for such a cluster aggregation process to occur? Well, again, if you think about your clusters living on a complete graph, you start with monomers at every side of the complete graph. Once a cluster size, say, reaches 100, that means that roughly 1 out of every 100 sites is filled. So when I hop, 99 times out of 100, I'll hop onto an empty site and nothing happens. And 1 times out of 100, I actually hop and hit a site. And so the time I'll have to wait is 1 over the density of occupied sites on this complete graph. Now the last thing is that if my cluster, if the density is 1 over 100, that meant my size was equal to 100. So 1 over rho is also of the order of S. So this is S divided by S, which is 1. So from this, I get S dot is of the order of 1, and S is proportional to T. So that's kind of a little hand-waving argument to give you a feeling that we expect the typical cluster size to grow linearly with T. Okay, so what I want to do now is let's bring out the heavy ammunition, and I want to now solve these master equations, and I want to do it precisely, completely, with no funny business. And so the right way to do this is by the generating function approach. And so, again, I'm assuming that you saw some of this in your preliminary lectures. And I'm going to give you the exercise. I'll even tell it to you right now, which is that we all know and love the Fibonacci sequence. Use a generating function technique to solve for the nth term in the Fibonacci sequence. But why do we even use a generating function in the first place? Is that if you stare at these equations, you'll see that here, because of mass conservation, this is the form of a convolution. And when you learn in like elementary Fourier transform or Laplace transform courses, when you have a convolution in Fourier space or Laplace space, it turns into a product. The generating function is nothing more than a discretized version of the Laplace transform. So if you see convolution here, that should shout out to you, I should use the generating function because it converts the convolution into a product, and then it's easily soluble. So in the generating function, I'm going to write G for the generating function. Z and T is defined as summation k equals 1 to infinity ck z to the power k. And we're going to use that now to solve for the cluster mass distribution. Okay, so let's write our equations. Where shall I write it? I guess I'll put it over here. So we have ck dot is equal to summation ij restricted ci cj minus 2 ck sum ci. So what we do when we are trying to introduce the generating function, we want to convert this equation into a generating function equation. So what we do is we take this set of equations, we take the kth equation, multiply by z to the power k, and sum over all k. And let's see what happens. So on the left-hand side of the equation, we just have nothing more than the time derivative of the generating function. So on the left-hand side, we have g dot. Okay, on the right-hand side, so we have zk, we want to bring it into here. But zk, because k is I plus j, so zk is nothing more than zi, zj. And then we have sum ci, zi, sum cj, zj. And because we're summing over all k, we unrestrict the sum, and so we just have nothing more than the generating function squared. So here we have g squared. Here we have a 2, and then we have ck, zk summed over all k, so that's minus 2g. And then we have something else. We have sum ci. I can write that in a slightly perverse way. I can write it sum ci, zi, with z set equal to 1. So this is nothing more than the generating function at z equals 1. So what we've done now is we've transformed the entire infinite set of master equations to one equation. Unfortunately, it's not closed because it involves g of 1. But the way that we can simplify things, and allow me to be lazy now from here on in, I'll just call this g of 1. There's also, we can just put g equals, z equals 1, and so we'll get g of 1 dot is equal to g of 1 squared minus 2 g of 1 squared, which is equal to minus g of 1 squared. So in fact, we've reduced the entire infinite set of equations to 2 equations, one for g, which is not quite closed, and one for g1, which is closed. And so we can solve for g1, plug it back into here, and we have the full solution. Now, once you start playing this game, you want to try and simplify things as much as possible. And so it actually turns out to be a lot easier to let me write h as g minus g of 1. And so if you do that, you'll have h dot is equal to, so it's going to be g squared minus 2g of 1, and then minus g of 1 dot, so it's going to be plus and this is nothing more than h squared. So really, you can reduce everything to just a single equation. Isn't that cool? So we just have to solve that equation. So let me write this as, we can write this as dh over h squared is equal to dt. And so this I can, let me just, no, that's correct. So this is equal, so this I can write as 1 over h dot, actually, let me not save myself some trouble. So this is h dot over h squared is equal to 1. And I can write this as 1 over h dot is equal to minus 1. So even I can solve this equation, I think. So it's 1 over h minus 1 over h at t equals 0 is equal to t, minus t. So 1 over h is equal to minus t plus 1 over h at t equals 0. So we need the initial condition. And for the monomer-only initial condition, which again is all I'm doing throughout the entire lecture here, so at t equals 0, g is equal to C1, which is will be 1 for monomer-only condition, times z. So this is equal to z, and h which is g minus g of 1 is equal to z minus 1. So we have here minus t plus 1 over h, 1 over z minus 1. And so I can write this as 1. So this is the part where I oftentimes don't do very well. So if I make a mistake, just tell me. So what am I going to do here? So here I'm going to have 1 minus z minus 1, z minus 1t. I guess that's correct. So finally, h is equal to z minus 1, 1 minus z minus 1t. So I just want to do one example through the whole thing so you see like how, how it looks when you actually invert the generating function. Okay, so we're almost done. But we really want g, not h, because g was the actual generating function we're interested in. So we have to add to it g of 1. Now, I should have said this before, but so the equation for g of 1 was over here. And so g of 1 is the generating function at z equals 1. All right, I guess I have to do it because I can't sort of argue my way out of it. So let me do it. So we have g of 1 dot was equal to minus g squared with g of 1 squared. So that is also 1 over g1 dot is equal to 1. And so what we're going to get from all of this is 1 over g1 minus 1 over g1 at t equals 0 is equal to 1. So 1 over g is equal to 1 plus 1 over g1 t equals 0. I'm a bit lost, so just bear with me a moment. I kind of lost my train of thought here. Unless someone knows the answer. Sorry. I see what someone already told me what the right answer is here. So I want to integrate this thing. So this is t, not 1. And the generating function for monomer only condition was equal to 1. So this is equal to, so from this we get g is equal to 1 over 1 plus t. So finally, we're going to get the generating function, which is equal to h plus g1. So that's equal to z minus 1, 1 minus z minus 1 t plus 1 over 1 plus t. So this is our final answer for the generating function. Now, we're almost done, but we're not quite done because what we want is the cluster size concentration. So how do we get it from all of this? Well, in this case, it's fairly simple because we see that we want to just expand this in powers of z. This kind of smells like we might be able to expand it in powers of z. So let's try and do that. And so to simplify things, let me write this in the following way. 1 plus t, 1 minus z minus 1 times t. So I'll just put this over a common factor, and then I'm going to have z minus 1, 1 plus t, plus 1 minus z minus 1 t. And in the numerator, there's a lot of cancellation. And now let me just skip trivial steps because you'll see that I'm not really good at these sorts of trivial steps. Let me just write down the final answer because it's simple enough. So what we get here is 1 over 1 plus t, 1 over 1 plus t, and then there's the z up here, and then downstairs we have, so there's so 1 minus z minus 1t. Okay, so 1 over 1 plus t. Now let me you see here's 1 plus t. So let me factor out another factor of 1 plus t. So it's 1 plus t squared. Down here is z. And then I have 1 minus z times t, z times t. And I factor out a 1 plus t, so 1 plus t. Now we're in a situation that we can expand this in a power series easily enough. So this is equal to 1 over 1 plus t squared. And then have a summation. So there's a factor z sitting out in front of summation. K equals 0 to infinity, z to the power k, t divided by 1 plus t. But now ck is just the coefficient of the right power of k. Because there's an extra factor of k here, so I can write this like this. Sorry, k here. So finally, my answer is that ck of t is equal to, so I want the coefficient of z to the power k, so it's going to be t to the power, t divided by, I'll write it this way, 1 over 1 plus t squared times t divided by 1 plus t to the power k minus 1. So this is my final answer. So that is the cluster size distribution for constant kernel aggregation. Now, before we go any further, let's try and get some intuition for what this looks like and what sort of physical lessons we can learn from this exact solution. So let's first plot as a function of both time and space the cluster concentration. So let me plot ck. First, let me plot it as a function of time. So monomers, when k is equal to 1, this goes away, and it starts off just 1 over 1 plus t squared. So asymptotically, the concentration of monomers is decaying like 1 over t squared. It begins at 1, so here's 1, and this concentration is doing something like this. So that is C1. C2, well, it has the same 1 over t squared prefactor. For small time, it grows linearly with t. For large time, this factor approaches 1, and then this goes away, and then they go to a common value. So C2 starts off linearly and does something that looks like that. So here is C2. C2. Similarly, C3, well, it starts off quadratically and also approaches a common limit. So here is C3. And so on down the road. So as a function of time, all the cluster concentrations are asymptotically approaching a common limit, and they start off 0 power, 1 power, 2 power, to the k minus 1 power for ck. Similarly, we can look at as a function of k, ck. And in order to get a feeling for this, let me go back here and let's look what happens to this cluster concentration for large time and large k. So when the time is large, this factor I can write as 1 divided by 1 minus 1 over t, which I can write as, plus 1 over t, which I can write as 1 minus 1 over t, which I can write as e to the minus 1 over t. So asymptotically, this cluster concentration asymptotically goes like 1 over t squared, e to the minus, and if you allow me to be sloppy in the scaling asymptotic limit where I replace k minus 1 by k, it's just e to the minus k over t. So this latter form is what's called the scaling form of the cluster mass distribution. And as we're going to see in all kinds of problems in non-equilibrium stat mech, it's nice when you can get the exact solution, but exact solutions are far and few between. And when you can get the scaling solution, that's even better because somehow it provides you a more general insight into the problem. So basically, what the cluster mass distribution looks like is nothing more than exponential decay. So it's something like that. And there's a characteristic cluster size, K star, which is of the order of T, the typical cluster size. The overall amplitude is falling off as like 1 over T squared. And, you know, again, to try and make sure that everything kind of fits together, notice that if I integrate the cluster mass distribution up to the characteristic size T, there's an amplitude 1 over T squared. I'm integrating up to T. I'm getting a total contribution, which is like 1 over T. And that's just equal to the concentration of clusters themselves. So everything hangs together in this form of the cluster mass distribution. So that is the end of the exact solution of the constant kernel aggregation problem. So any questions before I delve further? Okay. Well, it's all well and good. We have the exact solution, but one problem with this exact solution in aggregation is that exact solutions are actually hard to come by. I mean, just as you know, like in the Ising model, the 2D Ising model, the state-of-the-art solution. Similarly, in aggregation kinetics, exact solutions are few and far between, and the only cases that have been solved exactly are the constant kernel, the sum kernel, Kij is I plus j, and the product kernel, Kij is I times j, and basically almost nothing else. So if we want to get a general insight into the problem, we really have to leave behind exact solution methods momentarily. What I want to now present to you is a scaling approach. And later on, I'm going to come back to exact solutions because I will come back and solve the product kernel exactly because the solution is so beautiful and so powerful, it's worth seeing. But let's now go to a scaling approach, which is in some sense more general and more insightful. So the idea is the following, which is that you try as mightily as you can to try and write everything in a scaling form, and from the scaling form, you try and infer some asymptotic behaviors. This is kind of a very vague statement that I just told you, so let me show you how you apply it for the diffusion equation. So here's a preliminary. The diffusion equation. So we have the equation dc dt is equal to d second c by dx squared. And what we're interested in is the concentration c as a function of x and t. Suppose you didn't know how to solve this equation. What could you do? Well, you know, if you just observe simulations of random walkers, you know that the probability distribution spreads out and spreads out. And so at later times, the distribution is more spread out. But if you look in the right frame of reference, the distribution actually is constant when you do everything in scaled units. So we know what this answer for CXT is, but let's suppose we don't know anything. So we do know, however, in a scaling approach that there's this sort of characteristic spread of the random walker, and if we use as our yardstick the actual spread of the random walker, the distribution looks self-similar. So let me call this characteristic size of the spread of the random walker, let me again call it S. And so this we might expect to be some function, a scaling function of x over S. So here S we can think of as a characteristic size of the random walk, which we know grows like square root of t, but let's not even assume that yet. This is not quite right as I've written it, because we know that this distribution is normalized. If I integrate over all x, we better get 1. As it's written here, if I were to take the integral of this function, dx, that actually would not be properly normalized because I could do 1 over s, multiply through by s, and then this is just some dimensionless number, and so we get the wrong units. So it has to be, in fact, that the scaling function has a prefactor out in front, which is exactly equal to 1 over s. So we can write this. This is the scaling form. And you can verify now that if I were to integrate this function over all x, you get a number of order 1, so it has the right normalization. So now we can, instead of trying to solve this directly, we can attempt a scaling solution. Let us assume that this is the form of the solution, and let's now plug it into the diffusion equation, well, let's see what comes out. So if I look at dc by dt, oh, by the way, I should mention that this characteristic spread of the random walker is some time-dependent quantity that we know is t to the 1/2, but let's assume we don't know it. So I should put here s of t to emphasize that it depends on time. So if I do dc dt, there's going to be two terms. There's a term where I differentiate the time here and one where I differentiate the time here. So here I'm going to get minus s dot over s squared times f. And now to simplify the notation, let me call this scaling argument. Let me define this thing to be u, so f of u. And then I have, when I differentiate inside of the argument itself, so I have plus 1 over s. And then I'm going to have f prime of u. And then I have to differentiate inside of here, so it's equal to minus x over s squared s dot. And so this is equal to common factor. There's a minus sign common, so there's an s dot over s squared. Then I have f of u. And here I have 3 powers of s, but I'm going to keep 1 power to combine with the x over s to make the variable u. So I have plus u f prime of u. So that's the left-hand side of the equation. On the right-hand side, we have d second c by dx squared. Sorry, my penmanship is slipping. D second c by dx squared. So when I differentiate with respect to x, I just bring down two, I take out 2 powers of s. So this is nothing more than d over s squared f double prime of its argument. So what we have done, oh, and I guess I've run out of room. I don't want to leave this blackboard, so let me just put it over here. So what we have then is, was there a question? Or you can't read it? No, it's okay. So I have d over s squared. F double prime is equal to minus s dot over s squared, and then I have f plus uf prime. And now what I can do is let me put all the time dependence on one side, all the u dependence on another side. And so what I'm going to get here is, yeah, you're right, okay. Oh, thank you. Thank you for saving my life. S cubed, S cubed. Thank you. Okay, so if we now, so I'm writing a little bit small. Can you guys see this over here? Not really, not really. Okay. I'll put it up here because I'm just at my final step. So what I got here is s dot times s. So I'm putting the s's on the right-hand side, so it's s dot times s, and so it's equal to d f double prime divided by f plus u f prime. And there is a minus sign. Notice that this is a function of time only. This is a function of u only. And from elementary differential equations, you know that if independent functions are functions of independent variables, they both have to be a constant. So let's call this constant equal to lambda. And now if we separately solve the equation ss dot is equal to lambda, we'll get s goes like t to the 1/2, which we know. And then I'll leave it as an exercise for you to do, but then if you solve this equation, you'll get a Gaussian function. So it turns out that the scaling approach reproduces, first of all, with no knowledge, the right scaling in time, and actually the full scaling function, and we get, in this particular case, we get the exact solution. So what I want to do now is apply exactly that same philosophy to the case of aggregation kinetics. So let's do that. So if we're going to be doing scaling where we're thinking about the long time asymptotic limit, it makes no sense to deal with discrete equations. So I'm going to write this for the continuous equation. So I will write ck. So now it's dck by dt. It's equal to integral 0 to x c yt Cx minus yt k y x minus y, and then there's minus integral from 0 to infinity Cx, this is x now, a continuous limit, minus Cxt, Cyt, k x y dy. Now, to make some progress, I need to make some assumptions about the actual reaction rate. And I'll make kind of the generic assumption which turns out to hold for essentially every physically reasonable aggregation process, which is that we're dealing with a homogeneous reaction rate. So homogeneity says that k of xy is such that when I take all masses and multiply them by some constant factor a, that the reaction rate is multiplied by some overall factor a to the lambda kxy. So this is the homogeneity assumption, and I'm going to use that then as as the input to then try and write a scaling solution for the cluster mass distribution. So next step is I have to now write a scaling form for the cluster mass distribution. So we saw in the case of the constant kernel aggregation process, by the way, if there's some questions, just ask me. I'm happy to answer. So, okay, anyways, so I want to write a scaling form for the cluster mass distribution. We've now seen in the case of diffusion, it gave us a hint about how we should write it. We might expect that Cxt should be some function of x divided by a characteristic cluster size. Right? So we saw in the case of diffusion, when there's a Gaussian spreading of the distribution function, if I measure the width of the distribution by the characteristic spread of the random walk, it's self-similar, so it's invariant with that ruler. Similarly here, if I rescale all cluster masses by the typical cluster size, we might hope that the cluster mass distribution goes to an invariant form, just as we saw over here. There's only one problem with this alleged form of the cluster mass distribution, which is that it's not properly normalized. In the case of diffusion, I had to divide by 1 over s to get something when I integrated over all space that I would get 1. Here, the normalization condition is a little bit different because we want to normalize it so that the total mass is conserved. The first moment of the distribution is conserved. And that forces me to write 1 over s squared. And you can verify immediately that if I now compute the first moment, so this ensures that x Cxt dx is equal to 1. So now I'm going to follow exactly the same program as I did over in the case of the diffusion equation, which is that we are going to now try to apply the scaling approach. And so so all we're going to do is we take this scaling form and this scaling form for the reaction rate, shove it into this equation, turn a crank, and let's see what comes out of all of this. And what you'll see is that, yeah, please. So the question you're asking is like, why is it the first moment is conserved? Because the 0th moment is definitely not conserved, because the 0th moment is, no, in the case of the diffusion equation, it's the first moment which is, I'm sorry, it's the 0th moment which is conserved, because that's just you have conservation of probability, the random walker isn't disappearing. But in the case of aggregation, clusters are disappearing, so the 0th moment is definitely not conserved. The first moment is the only conserved quantity, and any other moment is also not conserved. So the question was, when I'm doing scaling in general, like what do you have to take care of? And the point is that for every single problem, there'll be a different conserved set of quantities, and so you'll have to build that into your scaling form. So in the case of aggregation, the first moment is explicitly conserved, and that's what we have to take care of. Okay, so hopefully this is now going to look a little bit familiar. What I want to compute, first of all, is dc by dt. And so, again, the typical cluster size depends on time. And so I've got to differentiate this thing, and so there's going to be, when I differentiate the s, I'll get minus 2 s dot over s cubed times f of u. And then there's the term where I have 1 over s squared. And then I got to differentiate inside the argument. So there'll be an f prime of u, and then times minus x over s squared. And I can write this as, x over s squared times s dot. And so I can write this as minus s dot over s cubed, and then there's 2f plus uf prime. So that's the left-hand side. The right-hand side, well, that's a little bit more complicated, but not that much more complicated. Let me just do one of the two terms, because once I do one of the terms, the other term you'll see is just the same. Let's do the second term. So second term. So we have cxt. So we have the integral from 0 to infinity cxt. So that's 1 over s squared f of x over s. Then we have 1 over s squared f of y over s. And then I have kxy. And let me write this as k x over s, y over s. And because of homogeneity, I could transform from kxy to kx over s times y over s, as long as I multiply through by a factor of s to the power lambda. Right? And you can just check that what I did here is nothing more than just what I did here. And then I have to integrate over dy. I'm killing your chalk. I'm really sorry. Okay, so let's now put this in a scaling form. So in that first point, this is dy. Let me divide through, let me take one of the powers of s here and put it under here. So I'll write this as 1 over s and erase one of the powers here. So I'm doing something that if I was really lecturing in a real class, people would shoot me because, this is bad Blackboard, but I'm going to get away with it here. And so what I get here is there's a 1 over s cubed and s to the 3 minus lambda. And then I have integral from 0 to infinity f of u, f of v, dv. So things simplify because this is just some function of u, u only. So it's beginning to smell a little bit like what you saw over here, which is we're going to separate out the time dependence and the u dependence and separately solve for these things. So let me just put this together now. So what we're going to get is minus s dot over s cubed. And then I have 2f plus uf prime, And on the right-hand side, so it should come as no surprise that the first term also can be put in the same scaling form. And so it's going to be equal to 1 over s to the 3 minus lambda. And then I have integral from 0 to x. So that's x over s is integral u. Then I have f of y, which is v, f of u minus v, k of v, u minus v, minus integral from 0 to infinity, f of u, f of v, k u v dv. So it looks a little bit horrible, and it is a little bit horrible, but let's now try and simplify things. What we're going to get finally is s dot, s to the minus lambda. Let's put all the time dependencies on the left-hand side. Let's put all the u dependence on the right-hand side. And so we're going to have, by the way, this is brackets. We're going to have this function divided by that function. It's clearly just a function of u. And let me call that function h of u for a horrible function because it's a nonlinear integral operator, which I don't know how to deal with, but the point is it's a function of u. Here is t, here is u. So these separately both have to be equal to a constant. Let me call the constant capital lambda. So again, in the same framework as solving the diffusion equation, we've taken a horrible integral, nonlinear integral differential equation, and we've separated the variables, and we now have found the time dependence. So for general homogeneous kernels, we now know the average size of clusters. Even though we don't, we may not know the full distribution, we now have been able to compute the average size from this equation. So the average size satisfies s dot s to the minus lambda, where lambda is the homogeneity index, is equal to this separation constant, which I defined to be big lambda. And so there is three answers for how the s depends on time that comes from this. So for lambda less than 1, this goes as t to the power 1 over 1 minus lambda. Power law dependence of the average cluster size. So in the particular case of lambda equals 0, which constant kernel was part of that family, the average cluster size would just go linearly with t. But as you increase the homogeneity index, the cluster size is growing more and more rapidly. And you see that when lambda equals 1, something weird happens because this blows up. And in fact, when lambda is equal to 1, this grows like e to the lambda t. And for lambda larger than 1 and less than or equal to 2, the average cluster size has a finite time singularity. And so this goes like t minus t gel to the power 1 over 1 minus lambda. So we've gone partway through the general program of solving general homogeneous kernels, which is that we have found the average cluster size. Now the solution to this this integral equation, h of u is equal to lambda, in general we cannot do anything. And it turns out to be kind of a state-of-the-art calculation to make any progress. So let me just kind of briefly summarize qualitative behaviors that come from general homogeneous kernels. Yeah, please. Yes. Oh, thank you for that question. Yeah, so this is a time when the cluster size blows up. And so as we're going to see in in a few minutes, that there is a gelation time where like all the clusters coalesce into a macroscopic sized cluster. It's kind of like the percolation transition in the sense that you start with finite sized clusters and they can coalesce and make a macroscopic cluster in a finite time. Just as you get a infinite cluster at a finite value of p between 0 and 1. Anyway, so qualitative summary. So in order to write the qualitative summary, I need one more scaling assumption. So let me put it back over here, which is if k1j scales as j to the power nu. So this, I've written this, or let me write it as k1y, because I want to be in the continuous limit, y to the power nu. So it turns out there's three cases. There's this is not very good advertising, but there's so-called type 1, type 2, type 3 behavior. Lambda larger than nu. Then there's lambda less than nu, and lambda equals nu. So lambda greater than nu is kind of the conventional case. And this, you end up with a cluster size distribution that looks like this. So ck is a function of k. Well, maybe I should write log ck versus log k. It's some kind of a decaying power law distribution. Lambda less than nu, one ends up with so-called bell-shaped curves. And lambda equals nu is, let's just call this the weird case. And so there's not really much general you can say about it. So there's sort of a fundamental dichotomy between clustered mass distributions which have a decaying spectrum and localized or bell-shaped curve cluster mass distributions. All right, in the remaining time, I guess I am not going to finish this today, but I'll get close, is I want to now turn to something which is really beautiful, and that is the solution of the product kernel aggregation process. It's a state-of-the-art calculation, but it's state-of-the-art and beautiful. It's not state-of-the-art and ugly. So I'd like to try and present it to you because it's so impressive how you can get so much for so little. So I want to now turn to product kernel aggregation. Yeah, so lambda was the homogeneity index. And this index nu is just a measure of like, okay, so you asked a good point. Let me maybe come back here for a moment, which is that generically I can write ki or kxy. It's like an infinite dimensional matrix. And up here in the upper left-hand corner is like interaction between small clusters with other small clusters. Down here in the lower right is interaction of large clusters with large clusters. And then you have like small, large, and large, small. So this range corresponds to where large, large interactions dominate over small, small interactions. This range corresponds to these interactions, large, small, or small, large. So interactions between disparate sized clusters dominate over everything else, over large, large, and small, small. And this limit is where they're all the same order of magnitude. Does that answer your question? Not quite? I mean, this is, I am being a little bit vague here because in order to really develop an intuition, one has to solve specific models and see that this is what happens. But roughly speaking, why this happens, why there's this power law decay is that if large, large interactions are so much faster than everybody else, when I develop large clusters, they interact so rapidly that they leave behind a dust of the clusters that don't interact because the large, large interactions happen more quickly. Whereas in this case, where large, small interactions are dominating, so if there was a cluster here of this size, there would be a large cluster that would immediately scoop it up and it wouldn't be there anymore. And so that's kind of an intuition for why you have the two different types of. Oh, so lambda greater than 2 is a pathological case that corresponds to instantaneous gelation, which may be only of mathematical interest because it's hard to imagine a physical system with that happening, but that's what happens is that the gel time goes to 0, and it's really bizarre. Average size. No. This is referring to this. Average size is just S of t. Pardon me? Yeah. Yeah, somehow my title got moved in the wrong place in the blackboard. Okay, so let me now go to product kernel aggregation. So here I'm assuming Kij is equal to I times j. And the way we justify this kernel, like why am I choosing this? So I don't know if this is very popular in India, gelatin dessert, jello. Does everyone know what this is? So you take this powdered stuff, you pour it into a bowl, you pour water, you mix it up, you put it in the fridge, and about half hour later, it's turned from a liquid into a gel. And what happens is that each of the molecules it makes up in that powder is basically what's called a multifunctional polymer unit. So it's got like 3 grabby arms. So I only have 2 arms, so I can't really demonstrate it. But if I had 3 arms, I'd be grabbing, and I'd grab somebody here and grab somebody there. But each of you people have 3 grabby arms, and as we got larger and larger, we'd have more grabby arms. It would be very, very grabby, and so very quickly we would like span the entire classroom. So that is basically the motivation for choosing reaction rate Ij, is that you imagine that you start with monomers or like small clusters that have multiple grabby arms, and so the rate at which you come together is proportional to the product of your grabby arms proportional to Ij. So let's write down then the reaction rate in this case. So, or let's write down the master equation. So Ck dot is equal to summation Ij, Ici, JCj minus KCK summation ICI. And this is the restricted sum. So this is the problem that we want to solve. Now, notice that this infinite sum, ICI, is nothing more than the total mass in the system. So, and I've chosen my normalization, so the total mass is 1, so we can just erase that term. Oh, thank you. Thank you. Okay. So once again, you could try and solve these one by one. And if you try to do it solving by one, you'd find yourself kind of like lost very quickly. Somehow it doesn't work anymore. And so I want to present to you the generating function solution to this problem. And so let's solve by the generating function, because we saw how beautifully it worked in the case of constant kernel solution. So let's do the generating function. Now, one thing is that once you've played around with these sorts of problems, it's important to write the right type of generating function. Because you see there's like a factor I sitting below here, and the generating function was like ck z to the power k, and the way that you generate an I is you differentiate with respect to the parameter z. And because when you do that, there's one less power of z, it behooves one to write the generating function in a slightly different way. So I'm going to call the exponential generating function e of y is equal to summation over all k equals 1 to infinity. And I'll write it as ck, and beware, I left a space here for deliberate reasons, ck. Instead of writing it as z to the k, let me write it e to the yk. And you'll see in a moment why I did this. But it's really nothing. I just, instead of calling it z to the k, I called it e to the y times k. Now here comes one more trick, which is I'm going to put a k here in front. I'm free to do this if I want to. And if you did not have the foresight to put a k here, so I leave it as an exercise for you to do it on your own, which is don't put a k here, and go through the same solution steps, and you'll find very quickly you'll end up with, I should have put a k here in the first place. It'll become obvious, when you go through the solution. So let me put a k here to begin with. And now let's try and write the equation for the generating function. Okay, so we take our equation, we multiply by k, e to the y, k, and we sum over all k. So on the right-hand side of the equation, we have dE by dt. So let me write this as e. I'm going to be lazy now. I'm going to write subscript for partial derivatives. So that's et. And over here, let's see what we have. So let's do the second term first. So we have k squared ck e to the yk. And so k squared ck e to the yk, that's almost this with one extra power of k. So on the right, we're going to have minus dEy. Right? When I differentiate one with respect to y, down comes an extra factor of k. So that gives me k squared ck e to the yk. So now we have to do the left-hand side. And so here I have I have I, j, and then I have k, which is I plus j. So I plus j. Then I have e to the y, I, e to the y, j. And then I want to sum over everything. So let's see what comes out of all of this. So there's a term here, I squared e to the yi, which is nothing more than the generating function derivative with respect to y. And then there's a term j, e to the yj, which is a generating function. And I have, oh, I made a mistake, 1/2 here. I forgot the 1/2. So I have a term again, I squared e to the yi, which is the derivative of the generating function, times j e to the yj, which is the generating function itself. I have two such terms that cancels the 1/2. And so I have a term here which is ey. So I have the differential equation et is equal to EY times E minus 1. So that is it. I've transformed my infinite set of master equations into a single partial differential equation. Some of you may recognize this equation. It's the Burgers equation. And let me show you how you solve this, because it's one of these things that it's straightforward, but if you haven't seen it before, it's like straightforward but amazing. So the way you solve, there's many ways you can solve the Burgers equation. One way you can solve it is by the method of characteristics. And so when you take undergraduate differential equations, I don't know about you, but this is what I've learned about it, is that someone talked about the method of characteristics. I completely forgot about it until I was faced with this equation, and finally I learned it. So anyways, so we have ET is equal to, let me write it this way, plus 1 minus E dy is equal to 0. How do we solve this method by the method of characteristics? We each want to try and write this as a total time derivative. Notice that dE by dt, and here let me be careful of putting the arguments, d of E and Y and t, the total time derivative is equal to two terms. It's dE by dt, so now I'm not being lazy. I'm going to write the derivatives explicitly. So there's that term. And then there's plus dE by dy by dt. That's equal to 0. So, along the curve, defined by dy by dt is equal to 1 minus E. E is equal to a constant. So if we can just, so if we live along this curve, E is equal to a constant. So when E is equal to a constant, and with respect to this curve, it means that E is independent of T. So that means that Y is equal to, so Y of T is equal to 1 minus E T plus some constant. And that constant is determined by the initial condition. And what is the initial condition? So at T equals 0, this is 0, and so we have Y is equal to its initial value. And now I go back to the definition of the generating function. And so notice that at T equals 0, E of Y and T equals 0, well, at T equals 0, there's only monomers. So the sum is one term, C1, which is 1, E to the Y. So this is equal to E to the Y. So my initial constant, Y, is just little y is log E. So here we have 1 minus E T plus log E. So we're done. We have the solution. So we have, so let me write this now, put it over here. So we have E, times E to the 1 minus E T is equal to E to the Y. Or E to the minus ET is equal to E to the Y minus T. And because I know what I want to get, let me write this as ET, E to the minus ET is equal to T, E to the Y minus T. So this is the solution for E of T. It's perfectly true solution, but it's completely useless because, it's like implicit. We have T as a function of E, but we want E as a function of T and Y. So we're kind of stuck here. But, and now let me show you, I've got 5 minutes. So in 5 minutes, I'm going to show you some black magic. And for those of you taking a course in complex analysis, it may not be so black magic-y, but I assume everybody knows about like Cauchy integration formula, complex plane, integral in a complex plane. So let me call this thing capital, so let's call this capital Y is ET, and this is, let's call this capital X. So we have the equation Y e to the minus Y is equal to capital X. So well, we have x as a function of y, but we want y as a function of x. And so we want y as a function of x. So we want this as some power series in x, a n capital X to the power n. So if I could write it, if I just write it as a power series formally, we know how to compute a sub n. A sub n is nothing more than 1 over 2 pi I, the integral of y divided by x to the power n dx. Right? It's just the Cauchy integration formula. If I want the nth term in the power series, I just divide by x to the n plus 1. So that's the residue in this integral here. Now, as it stands, well, that looks pretty damn horrible. And in fact, because we don't know what y is. So how can we do anything with this? And so here comes the black magic, and this is called the Lagrange inversion formula, which is that, well, I don't know what y is, but why not just exchange our two variables? Because for small x, notice here that when x is small, here is that x is proportional to y. So when I'm looking, and since I can deform my contour, it's a closed contour around the origin, I can take it infinitesimally small. So I can exchange variables between x and y. So I'm going to just do x. I'm going to change integration variables between x and y. So I write 1 over 2 pi I, Cauchy integral, y divided by x to the power n. And I'll write here dx by dy, which I know how to compute because I have x as a function of y, dy. And so I have 1 over 2 pi I, Cauchy integral. And so I have y, yes, thank you, x to the power n plus 1. Thank you for keeping me honest. Y over x to the power n plus 1. And so I have dx by dy. So when I differentiate x with respect to y, so here it is. When I differentiate with respect to y, I have two terms. I have e to the minus y. When I differentiate the y there, and then there's minus y. Okay, it's easier to write it this way. 1 minus y, e to the minus y, dy. And now y, so let me get rid of the x here and write this as y e to the minus y to the power n plus 1. So now in this form, we don't have to do any contour integration because now we can expand this in a power series in y, and we can identify the nth term in the residue with no work. And so I'm just going to write down the answer, and I leave it as a simple exercise for you to do because I'm out of time now. I've got 90 seconds left to go. So it's it's n to the n minus 1 over n factorial. Let me check. N to the n minus, it's even right. Okay. So that's a solution. And so now that we've found what a sub n is, we can then extract the cluster concentration because, we want, so y, so again, we have y, which is et. So therefore, we have that et is equal to summation an, which is n to the n minus 1 over n factorial times x to the power n, and x was e to the ny minus nt. And so let me just, because I'm out of time, let me just write down the answer for the cluster size distribution. And next time I'll analyze its asymptotic properties. So this turns out to be k to the power k minus 2 over k factorial e to the minus kt t to the power k minus 1 is what it is. I think that's correct. Yes. And this is k factorial down here. So please. Louder? Say that again louder. Right. Oh, because E, remember that, I'm sorry, I mean, I'm rushing because I'm out of time here. This E was nothing more than summation CK, where is it? It was equal to summation K CK e to the YK. So I plugged that in here, and then I compared these two terms, and what? Just say it louder. Right. To the what? Oh, t to the power n. I'm sorry. Oh, because you're saying, oh yeah, there's t to the power n. Thank you. Thank you. Yes, I just copied from here. I went. Okay. So, I don't know. I mean, this is when you're first exposed to some of this stuff here. I think it can seem a bit overwhelming, but it's actually kind of, I'm applying nothing more than standard tools of an advanced undergraduate class, differential equations and complex analysis. But what I like about this is that it's so beautiful. I mean, like with, that how to go from this set of infinite equations to this Burger's equation, how you solve it. You expose, I don't know if any of you have ever seen the Lagrange inversion formula, but if you've never seen it before, play with it because it's so beautiful and so powerful. And it just gives you a taste of like some of the mathematical tools that you need to start to master to actually be like, in some sense, a real theoretical physicist. So I didn't quite finish what I wanted to do, which is analyze the asymptotics of this. So I'll do that next time. And as I said, I'm going to be jumping around and giving you sort of paradigmatic examples. So I'll then go to the problem of treating irreversible adsorption. So it'll seem very disconnected, but I hope you'll see the unity in some of the methods that I'll be using. So thank you. And so questions, ask away. Yes. Well, when you say equilibrium version, well, if you had aggregation with disaggregation happening at the same time, so clusters could join and they could break apart, then you would go to a steady state. It actually is not an equilibrium system because there's always a flux of particles that are aggregating and flux of particles that are disaggregating. But then one can analyze the problem of reversible aggregation. And so this is also a very well-studied problem. But let me just mention, from the point of view of social dynamics, another example of where aggregation appears is in social dynamics. Is that, I don't know how many people in this room know each other, but by the end of the 2 weeks, there'll be little clusters of friends that'll formed, and maybe you'll start emailing each other and know each other for the rest of your lives. But this also happens in the stock market. Like I might be like, while I'm lecturing, I'm looking at my phone and saying, oh, like I should buy some shares of Tata because like it's a really growing company. And then people look over my shoulder, he's buying Tata, I should buy Tata. And then all of a sudden the stock price goes up and then there's a big crash, and then we all like say, oh, this was horrible, I'm never gonna do this again, and we don't ever talk to each other. So you can have both aggregation, social aggregation, and social disaggregation. So there's all kinds of phenomenology that involves both clusters aggregating and clusters falling apart. And so it's a very rich subject, and it has been studied for 70 or 80 years, but all of its ramifications have not been fully explored.